Welcome back, everyone. This week we're going to continue our discussion of functions, and we're going to start talking about special kinds of functions. Just as a small preview, in this video we're going to talk about one-to-one functions. So we'll talk all about what those are, how to prove a function is one-to-one, is not one-to-one, all of that kind of thing. And I'll go ahead and tell you now that one-to-one functions are also called injective functions. Now, every once in a while you'll hear me use the word injective. I will do my best to always say one-to-one, but it slips out now and then. But you'll see various other faculty members in other classes will prefer the term injective, which is just fine. It means exactly the same thing, so you are warned for now. In the next video, then, we're going to talk about something called onto functions, which is a completely different property that functions might or might not have, and in that video, we'll talk about how to show that a function is onto or isn't onto, and all of that kind of good thing. And I'll note for the future that onto functions are also often called surjective functions. And so, you'll often see people, maybe sometimes you'll catch me doing it, but you'll often see people refer to onto functions as surjective. The words mean the same thing, just different words have gotten into common usage. The video after that, we're going to talk about what are called bijective functions. And now, you might from the name think, oh, this is just going to be another kind of function, and in a way it is. But I'll go ahead and tell you now, what a bijective function is it's one that's both injective and surjective, which is sort of the etymology of this word. It's both jectives, if you want. But it's just a function that's both one-to-one and onto. And so we'll spend a video talking about what's special about functions that meet both of these criteria. Now, really, between what we're going to say about one-to-one functions, onto functions, and bijective functions, that's going to be the majority of the week, and it's going to be the majority of what I have left to say about functions. But, inevitably, at the end, there'll be a few things that I haven't yet talked about, and so I'll make extra sure that we have sort of a video at the end that's sort of a tail string of thoughts about things you should know about functions just going forward, because they might show up. But, without further ado, this is the one-to-one functions video, so I'm going to start by defining what it means for a function to be one-to-one. So here's the definition. We call a function one-to-one if every pair of elements of the domain, so note A here is the domain, satisfy the following implication, or make the following implication true. Namely, if f of x equals f of y, then x equals y. Now, remember what it takes to make this implication true. Namely, this implication is true if the if part is false, right? So if f of x is not equal to f of y, whole implication's automatically true. But if f of x is equal to f of y, then it must follow that x equals y. That's really what this implication here is saying. Again, this comes back to our definition of implication. So for lots of pairs of x and y, presumably f of x is not equal to f of y, and then this implication is just vacuously true. In terms of understanding what this definition really means, I think it actually makes a lot more sense if we write down the contrapositive of this implication. Now, because an implication is logically equivalent to its contrapositive, this definition would be exactly the same if I replaced this contrapositive in for this implication here. And that lets me read this most straightforwardly. Namely, what does it mean to be one-to-one? It means if you take two different inputs and put them into the function, you get two different outputs. Now, I'm going to go ahead and tell you right now that both the original statement, the way I wrote it, and the contrapositive are very useful in different instances. So it's important to understand both of these and be happy to flip between them. Most commonly, you'll use the version I wrote up here as the original definition to prove a function is one-to-one, and you'll use the negation of the contrapositive to show that a function is not one-to-one. So this function, for example, is one-to-one. Every pair of elements that are different map to a different pair of outputs. This function, though, this is not one-to-one. And why is it not 1-to-1? It's not 1-to-1 because both of these inputs have the same output. In terms of arrows, one way you could frame this is to say that a function is not 1-to-1 if two arrows point at the same place. Or, conversely, it is 1-to-1 if no two arrows point at the same place. So before we move on, let's write down the definition of what it means to not be 1-to-1, just so that we're clear. So here I am taking this definition, and I am just copying it, except that I'm going to negate it. And so now let's carefully practice our negating. So this is if for every x and y in A, the following implication is true. And so here it's going to be, instead of for every, it's going to be there exist. And it would be there exist x and y in A, so that this implication is false. Or, if you prefer, such that this implication is false. And that's usually the more useful version. And so, what is the negation of an implication? Here is where it's important to remember that the negation of P implies Q is P and not Q. So in this case, there exist x and y in A, such that x is not equal to y, and the negation of f of x is not equal to f of y, f of x is equal to f of y. This is almost exactly what I was trying to show you here intuitively, that it meant to be not 1-to-1. Namely, it means there's two inputs that map to the same output. So we're going to do a lot of exercises of the form, here's the function, decide if it's 1-to-1, prove your answer. And I'd like you to take a moment, just ask yourself, when I ask you that, what is it you hope the answer is? Do you hope that the function is 1-to-1? Or do you hope that the function is not 1-to-1? And your answer should be that you hope the function is not 1-to-1. How do I know that I hope the function's not 1-to-1, even though I've given you basically no examples of this? And the reason why you should know that you want to show something is not 1-to-1 is that something not being 1-to-1 has a there exist quantifier. Whereas, if you compare that to the definition of something being 1-to-1, that has a for every quantifier. And so remember, if we're going to show something is true, we would almost always prefer it be a there exist quantifier than a for every quantifier. Okay, so let's do a couple examples, just to get our head around this, of deciding whether some functions are 1-to-1 or not. So pretty much always when I'm doing something like this, I'm going to start with our favorite function from calculus. Good old f of x is x squared. And so my question is this function 1-to-1? Or, alternatively, is it not 1-to-1? So again, everything either is 1-to-1 or is not 1-to-1. So in other words, this statement of the original definition, or this statement of the negation of that definition, one of them is true. Which of them is it that's true? And probably, if you think about it, you can convince yourself the one that's true is the negation. Namely, the function from r to r that takes x to x squared is not 1-to-1, because, in fact, there exist two elements in the domain which are different, but map to the same element in the codomain. Namely, if I take, for example, f of 4, I get the same thing as if I take f of minus 4. Both of these give me 16. And this is really all I need to show that something's not 1-to-1. I need one pair of different inputs that have the same output. Now, while we're on this, if you try and think about, okay, x to x squared is definitely not 1-to-1. Think through your other favorite calculus-y functions. And so you can think about e to the x, and log of x, and the trig functions, and all of these sorts of things. And if you're getting what it means to be not 1-to-1, you should see pretty quickly none of the trig functions are going to be one-to-one if you take them on their natural domain. For example, if I take x maps to sine of x, I'm definitely going to be able to find different inputs that map to the same output. In fact, basically, what the fact that sine of x is periodic tells you is that the same outputs keep happening over and over and over and over again. And so in a sense, periodic functions like sine of x or cosine of x are about as un-one-to-one as it's possible to be. So here are two inputs to sine that give you the same output, sine of 0 and sine of 2 pi. Now, of course, not all functions that we're going to talk about are going to involve the real numbers. Lots of functions we're going to talk about are going to involve other sets. So, for example, I'll call this function d. Namely, what does this function do? It takes a pair of positive integers and, well, divides them. So basically makes the rational number with p as the numerator and q as the denominator. So, is this one-to-one, or is it not one-to-one? In other words, what I'm asking is it possible to find two inputs to this function that map to the same place? Or is it true that no matter what pair of inputs I put in here, as long as they're different, I'll get something different out? And in fact, I think you will figure out, if you think about it carefully, that d is not one-to-one. For example, I claim d of 3, 4 is the same thing as d of 6, 8. What's that saying? Well, that's really saying that the fraction 3/4 is the same as the fraction 6/8. And so actually, the fact that this function is not one-to-one is sort of an expression of this failure of the rational numbers to have a unique representation. Namely, not all rational numbers are in lowest terms if you write them in a particular way. So if you write something as 6/8, it's not wrong, but it could be better written as 3/4. We're going to be particularly interested, when talking about these kinds of functions, with what happens when both sets involved are finite. So, for example, if A is the set 1 through 7, and B is the set, let's say, 2 through 6, and the reason why finite sets end up being interesting is that sometimes there's not a one-to-one function from a finite set to another finite set. So if I choose this A and this B, I claim there's actually no one-to-one function from A to B. And if you think about what this would look like in terms of pictures, you might see why. There's the 7 elements of A. There are the 5 elements of B. And when I say there's no one-to-one functions from A to B, all I'm really saying is it's impossible to send all 7 of the elements of A to a different element of B. And why is that? Well, that's because there are 7 different elements of A, but only 5 different elements of B. And so it's kind of a simple observation, but in fact, in order for there to be a one-to-one function from a finite set A to a finite set B, there have to be fewer elements in A than there are in B, or at least an equal number of elements. And this observation is something called the Pigeonhole Principle. Now, as we continue our discussion about functions, there are going to be a lot of pigeonhole principles. So I will call this the Pigeonhole Principle Part 1, and there's going to be 4 parts in total, but you don't need to remember the numbers, you just need to remember the content of what they say. So here's what the Pigeonhole Principle says, or at least one way of saying it, which is that if I start with 2 finite sets, then there exists a one-to-one function from the first set A to the second set B, if and only if the number of elements in A is less than or equal to the number of elements in B. Now, I really hope that this feels so obvious in a way that you're not now saying, like, okay, well, how do you prove that? Because actually, this really cuts to the core of what numbers and counting are. And, in fact, really it cuts down to the core of what it means to say a number is less than another number. What does it really mean to say that 3 is less than or equal to 5? Well, it means if I lay out 3 things in a row, and then I lay out 5 things in a row next to it, the 5 things stretch out further than the 3 things. And so if you take, for example, my 3 markers as one set and my 5 markers as the other set, and I've just laid them out like this, how do I write down a one-to-one function from the set of 3 markers to the set of 5 markers? Well, I send this orange one to this black one, this yellow one to this blue one, this red one to this black one, and that's it. That's a one-to-one function. I just don't use those, but that doesn't matter because they're in the codomain. Now, you may well ask, why is this called the pigeonhole principle? What's actually going on here? And so, to explain that, I have to first show you what a pigeonhole is. And so back when keeping pigeons was a popular hobby, they would usually be kept in boxes like this. And each one of these individual boxes was called a pigeonhole. And so if you think about it, what's really happening when each pigeon claims its pigeonhole is that you're getting a function from the set of pigeons who inhabit your area to the set of pigeonholes that they inhabit. But because the pigeonholes are small, it's not just any function, it's a one-to-one function. Because 2 pigeons can't live in the same hole. The hole is not large enough. And so with all of that set up, what is it the pigeonhole principle really says in terms of pigeons? It says that if every pigeon lives in one pigeonhole, then the number of pigeons you have is less than or equal to the number of pigeonholes you have. And so again, this is saying something that I think is intuitive and clear, but has very profound and important implications, and ends up being way more useful than it ought to be for what it looks like. Now, as with everything I will call a pigeonhole principle, be it 1, 2, 3, or 4, the hypothesis here is that all the sets involved are finite. So the second a set is infinite, we do not know how to make sense of this pigeonhole principle. So, if you're going to apply the pigeonhole principle, the sets you're going to apply it to had better be finite sets. Now, a little tiny preview. When we go to talk about the cardinalities of infinite sets next week, we're going to take inspiration from this pigeonhole principle and the other ones to try and understand what our definition should be about talking about infinite sets. But please just remember, you can never apply the pigeonhole principle to an infinite set. Let me write down an immediate corollary of the pigeonhole principle for you that is often the one we're using, and in fact, it's the version that we used really to say that there's no one-to-one function from A to B if A is the numbers from 1 to 7 and B is the numbers from 2 to 6. Namely, that corollary is, if A and B are finite sets, and the cardinality of A is larger than the cardinality of B, then there is no one-to-one function from A to B. Now, in fact, this whole circle of ideas is so important, I'm also going to write down the contrapositive of this corollary. And the contrapositive of this corollary is that if A and B are finite sets, and f from A to B is a one-to-one function, then the size of A is less than or equal to the size of B. All of this whole circle of ideas, all of them get called the pigeonhole principle. So let's think about this statement that's pigeonhole principle-esque, and I want you to decide if you believe this. So here A and B are finite sets, and I want you to decide if you believe that if A and B are finite sets, and the size of A is less than or equal to the size of B, and f from A to B is a function, then f is 1-to-1. And this, I want to emphasize, is not true. And so if I want to convince you it's not true, I have to give you a counterexample. So here is a counterexample. Here is my set A. It contains 1 and 2. Here's my set B. It contains 1, 2, and 3. And I'm going to write you down a function from A to B that is not 1-to-1. In order to describe a function from A to B, note I just have to tell you where 1 goes and where 2 goes. And in fact, the function I'm going to write down is going to take 1 to 3. It will also take 2 to 3. And this is definitely not 1-to-1, right? Namely, both of these are different, but they both map to 3. Again, it's worth checking why does this thing I've written down, that's even super strong because it's an if and only if statement, why does it not tell me that this statement written in blue is true? And there are some magic words sitting in this statement of the Pigeonhole Principle that tell me it's not going to give me this. And those magic words are, there exists. Because the size of A is less than the size of B, the Pigeonhole Principle guarantees me that there exists a one-to-one function from A to B. Sure. For example, I could send 1 to 3 and 2 to 2. That would be a one-to-one function. There is one. Great. It certainly does not guarantee me that every function from such a set is one-to-one. Just that there is a one-to-one function. I know we keep coming back to understanding the quantifiers, but it's really important to distinguish these in our minds. We've put this off long enough. Let's start proving things are one-to-one. For this, we're going to want to come back to our definition, which is that a function is one-to-one if every pair of elements in the domain make the following implication true. So every pair of elements in the domain make this if-then statement true. And I'm just going to most often use a direct proof to show you this. Okay, so I'm going to spell out what it is I want to show. Namely, I want to show that if I take two elements in the domain, and they happen to give me the same output in the codomain, then in fact the two inputs were already equal. That's what I want to show. And so I've written out this want to show explicitly just so that we already know what the proof structure is going to be. Namely, we're going to suppose the if part, do some work, and get to the then part. So I'm going to suppose that x and y are integers, and f of x is equal to f of y. And I'm going to write out what that means. Namely, that is saying that 3x minus 7 is equal to 3y minus 7. But if 3x minus 7 is equal to 3y minus 7, I can add 7 to both sides, and that will tell me that 3x is equal to 3y. But once 3x is equal to 3y, we can divide both sides by 3, and that will give us that x is equal to y. And now, that's what we wanted to show, so we're done. To prove a function's one-to-one, we're always going to use this format. But this format requires a little bit of caution. So let's look at a similar exercise here. So let's try and do the same thing we just did. So let's suppose x and y are in Z, and f of x is equal to f of y. Then 3x squared minus 7 is equal to 3y squared minus 7. So 3x squared is 3y squared. So x squared is y squared. So taking the square root of both sides, x is y. And then we're done. Now that all looks good. And unfortunately, no giant thunderbolt stopped me from writing it, but this is completely bogus. How do I know it's completely bogus? Well, one way I know that it's completely bogus is that this function's not one-to-one. How do I know it's not one-to-one? Well, if I were to take, say, f of 2, that would be 3 times 2 squared minus 7, and that's 5. But if I took f of minus 2, that would be 3 times minus 2 squared minus 7, and that is also 5. And so f of 2 is in fact actually equal to f of minus 2. And as soon as you see that f of 2 is equal to f of minus 2, well, you know this function's not one-to-one. So, what was wrong with this proof? Because the counterexample and the proof can't both be right. And the part where something went horribly wrong was actually at the very, very end. The last line. So I had x squared is equal to y squared, and so I said take the square root of both sides, and you'll get x is equal to y. That would be all well and good if it was actually true that the square root of x squared was equal to x. But it's not true. For example, if x was -3, -3 squared would be 9, and the square root of 9 is +3, not -3. And so basically what's going on here is there's no way for the square root of x squared to sort of remember that the x I started with was actually negative. It completely loses the sign, because square root, by our convention, always gives us back the positive one of the square roots. And so what's actually the true statement? The true statement is that for all x and r, the square root of x squared is the absolute value of x. That is, when you take the square root of x squared, you retain all the information except for the sign. The SIGN sign gets lost. So, if you had been thinking about this correctly, when you got to x squared is equal to y squared, you would be quite welcome to take the square root of both sides, which would tell you that the absolute value of x is equal to the absolute value of y. But then you have to be careful, because knowing the absolute value of x is equal to the absolute value of y does nothing to tell you that x is equal to y. So the moral of the story is that we must use caution. Next, I want to point out how sensitive whether a function is one-to-one is to all of the pieces of information that you're given. Namely, in the example we just did, we saw that if we looked at the function from z to z that took n to 3n squared minus 7, that it was not one-to-one. And I showed you that by writing down a particular example of two inputs, 2 and -2, that happen to map to the same place. But if you look now, in this new version, I have lopped off half of the domain. Namely, I took away 0 and the negative integers. And in particular, that removed my counterexample from before. It is no longer possible for me to write down f of 2 equals f of -2, because this function doesn't even have an f of -2. And so now, this function actually is one-to-one. But I need to figure out how to prove that. And I think the easiest way to go about this is to start almost exactly the way we started our wrong proof earlier. But I think this is actually easiest if we resist the temptation to take the square root of both sides, and instead subtract the y squared to the other side. And so what that allows us to do is to factor this as x minus y times x plus y is equal to 0. Now, we have our product of two things being equal to 0, and so from that, we get that x minus y is equal to 0, or x plus y is equal to 0. But because x and y are in z plus, I actually know x plus y is not equal to 0, right? X plus y is strictly positive. And so what that ends up telling me is that in fact x minus y is equal to 0. Remember, we knew x minus y was equal to 0 or x plus y was equal to 0, but we then showed this part of the or didn't happen, so then this part must have happened. It basically comes from the truth table of or. And once we have x minus y is equal to 0, that gives us x is equal to y after adding y to both sides. And then we're done. Here's a new function. This one's going from r to r cross r, or r2 if you prefer. And we're taking a particular input t, that is a particular real number t, and we're sending it to t minus 3 times the sine of t, comma, t plus 3 times the sine of t. Now, I don't blame you at all if you have no idea what this is describing, but this is really just a parametric equation. And if you pull open Desmos, in fact, this is what the graph of this more or less looks like. And so as the input t varies, we sketch out this curve. So the graph probably did not really help us answer the question. Is this one-to-one? Maybe, maybe not, who knows? If you have no idea, often the best thing you can do is try and prove it's one-to-one. And then sometimes if you fail to prove it's one-to-one, you'll actually learn from failing to prove it's one-to-one what an example is of why it's not one-to-one. Or you might succeed in proving it's one-to-one, in which case, great, you win there too. So let's try to prove that this is one-to-one. Note, I've kept to x and y here. If you like, you could make your variables s and t. Of course, the names of the variables are completely irrelevant. So let's suppose we have these two things and those are equal. What does that mean? That means that x minus 3 sine of x, comma, x plus 3 sine of x is equal to y minus 3 sine of y, comma, y plus 3 sine of y. And I actually have to pause for a moment to think what it even means to say these two things are equal. Because quite likely, you've never seen an equal sign sitting between two ordered pairs before. But what does it mean? If two ordered pairs are the same, it means the first slots are equal and the second slots are equal. So when I say these tuples are equal, what I'm really describing is a system of equations. Namely, the system of equations, x minus 3 sine x is equal to y minus 3 sine y, and x plus 3 sine x is equal to y plus 3 sine of y. Now, a trick you'll often see with systems of equations is that often you want to sort of combine the systems of equations to get you something better. So in this case, I want to add these two equations. So that is to say, the left side equals the right side here, the left side equals the right side here. So if I add the left side here to the left side here, and the right side here to the right side here, then the thing should still be equal. And in fact, when I do that, there's a great deal of cancellation. Namely, when I take x minus 3 sine x plus 3 sine of x, the 3 sine of x completely disappears. And so in fact, all we're left with is 2x is equal to 2y. And so that gives us x is equal to y. And in this instance, we happen to have shown the function's one-to-one, right? We supposed we had two inputs that mapped to the same output, and we actually ended up showing, hey, those were the same input. Ta-da! Last, I want to show you one trick that shows up a lot for proving that a function from R to R is one-to-one. So here's our function. X maps to x to the fifth plus 5x cubed plus 7x plus 4. And so it might be really tempting here to set f of x equal to f of y and try and solve it. However, I'd encourage you to try it, but it will be a disaster. Because there'll be so many terms floating around, and there'll be these giant degree 5 polynomials, and you'll have to find all sorts of identities about factoring the difference of fifth powers that you probably do not want to think about. And so it's not clear exactly how to proceed. So here, for functions like this, there is actually an alternative method. And the alternative method involves thinking about what the graph of this function would look like. And in particular, one way we might think about what the graph of this function looks like is to think about its derivative. Namely, the derivative of this function is 5x to the fourth plus 15x squared plus 7. And that doesn't look a whole lot better than f itself, but actually if you squint, one thing about this derivative might jump out at you. And that's that there are only even exponents and positive coefficients. So in fact, this is strictly greater than 0 at all places. And what do we know about a function whose derivative is positive everywhere? Well, a function whose derivative is positive everywhere is everywhere increasing. But, and I'll leave this as a homework exercise, it's impossible for an increasing function to not be one-to-one. And if you think about it intuitively, that kind of makes sense, because if I have a function that's increasing, but I want it to not be one-to-one, that means I've got to repeat an output, like maybe I repeat that output. But how do I repeat that output while still being increasing? And so for functions specifically from R to R, often the way you end up proving that they are one-to-one is to prove that their derivative is always positive or always negative, so that they're increasing or decreasing, and then that will tell you that the function is going to be one-to-one. on the homework and on the exams, this is not the kind of proof I'm looking for because this isn't really a calculus class, but you're likely to come across this in some subsequent class that's based on calculus, that this is an alternative way to show that something is one-to-one. In fact, actually, the idea of being one-to-one is so important that each area has its own little tricks. So if you've taken linear algebra, you might already have learned that a function is one-to-one if and only if it has trivial kernel. And if you don't know what those words mean, don't worry about it. Likewise, there's a similar version in abstract algebra, and so on. And so often, there are different ways of proving that something is one-to-one. But for us, we have a standard way, and we're going to use it. Very last bit. It's come up often in our discussions that a set is infinite if and only if there's a non-terminating, non-repeating list of elements of S. And it might have occurred to you to ask, well, mathematically, what is a non-terminating, non-repeating list of elements? Maybe that wasn't quite formal enough for you. So now that we have the language of functions, we can actually describe this really precisely. So let's start with what is a non-terminating list. You can think of a non-terminating list as really just being a function from the positive integers to your set. So if I have a non-terminating list of elements of S, well, I've written down a first one, send 1 there, a second one, a third one, a fourth one, and it goes on forever. And if I just keep repeating this process and write down each of those things, I'll get a function from Z plus to S. Now, the phrase non-terminating list, it is often in mathematics called a sequence, and so you might have seen that in Calculus 2, not to be confused with a series, which is the one where you add. A sequence is the one where you just have a bunch of commas in between. But a sequence of real numbers, for example, is just a function from the positive integers to the real numbers. So pause, think for a second. If I want to also add that the list is non-repeating, then what do I have to modify about the definition I gave here? And well, hopefully, having learned what we've learned in this video, I have to add that the function is one-to-one. So a non-terminating, non-repeating list of elements of S is really a one-to-one function from Z plus to S. So what this means is that going forward, whenever you're talking about a set, and what you know about the set is that it's infinite, you can replace that, or use that fact that it's infinite, to come up with a one-to-one function from the positive integers to that set. That's what being infinite really tells you about a set. At its foundation, it's telling you that there's a one-to-one function from the positive integers to that set. Alright, I'm going to wrap up there for now. In the next video, we'll talk about onto functions. And we'll do a similar discussion of how to show a function is onto, how to show a function is not onto, and we'll do a bunch of examples like we did today. But, until then, I'll see you next time.